Hi, in the previous module we talked about the multiple comparison problem that we're faced with when trying to threshold a statistical map. We talked about the family-wise error rate and the false detection rate. In this module we're going to go into more detail about family-wise error rate correction. The family-wise error rate, or the FWER, is the probability of making one or more type 1 errors in a family of tests under the null hypothesis. And so here a family of tests implies a series of tests. So in our case, we would have a family of, say, 100,000 tests, one corresponding to each voxel. Now there are a number of different family-wise error rate controlling methods that are used in the neuroimaging field. One is the classic Bonferroni correction. The second is random field theory. And the third are permutation tests. In this module we'll talk a little bit about the first two, and we'll leave the other one for reading on your own. So let's start out by formulating the problem. Let's let H naught of I be the hypothesis that there's no activation in a certain voxel I, where I belongs to some set V containing all the voxels. And so let's say there's lowercase m voxels in total. So H naught 1 is the hypothesis that there's no activation in voxel 1, H naught 2 is the hypothesis there's no activation in voxel 2, etc., etc. Now let's let Ti be the value of the test statistic at voxel I. So again, we have a hypothesis at each voxel, and we construct a test statistic at each voxel to see whether or not the data is consistent with the null hypothesis or not. And so these are the values that we have in our statistical map. Now the family-wise null hypothesis, which we're just going to call H naught, states that there's no activation in any of the m voxels. We can write this as H naught equal to the intercept of all the individual H naught of i's. So this implies that if we were to reject one of these H naught of i's, we would reject the family-wise null hypothesis. So it's basically just saying it's an omnibus null hypothesis saying that there's no activation in any of those. So basically all the H naught of i's hold. So if we reject the single voxel null hypothesis H naught of I, we're going to reject the family-wise null hypothesis. So a false positive at any voxel will give rise to what's called a family-wise error. So assuming that the null hypothesis is true, the family-wise null hypothesis, we want the probability of false rejecting H naught to be controlled by some value alpha, say 0.05. So we want to control the probability that any of the test statistics lie above some threshold u. So if any of the test statistics lie above this threshold, we'll reject the null hypothesis and we'll get a false positive. And so we want to make this probability as small as possible. We want to make it less than or equal to alpha, some predetermined value of alpha. The classic way of doing this is doing something called Bonferroni correction. So in Bonferroni correction, we choose the threshold for each individual test so that we control the probability of making a type 1 error to be less than alpha divided by m, where m is the total number of tests that we're performing. In this case, 100,000, let's say. So for each individual voxel, we want to choose a threshold u, so the probability that Ti is bigger than or equal to u is less than some number alpha over m. According to this criteria, the family-wise error rate, which is the probability that any of these test statistics is above this threshold u under the null hypothesis, can be expressed according to Boole's inequality as being less than or equal to the sum of the individual test statistics being above this value u. Now this, according to the threshold, is less than or equal to alpha, the sum of overall voxels over alpha divided by m, which is equal to alpha. So by using this Bonferroni correction, we're now controlling the family-wise error rate to be less than or equal to alpha, which is what we want to do. So Bonferroni correction provides a control over the family-wise error rate. And so this is one way we can choose our threshold u. We can determine alpha, say 0.05. We can divide that number by the number of tests, say 100,000. And then we can find the threshold for the test statistic for which the probability that the test statistic exceeds that value under the null hypothesis is less than or equal to alpha over m. Here's an example. So let's suppose that we generate 10,000 voxels. So this is a 100 by 100 image of voxels from an IID normal 0-1 distribution. So if I were to threshold it one-sided at u equal to 1.645, this would be equivalent for each individual test an alpha value of 0.05. In this case, you'll see that significant voxels are white and non-significant are black. We see that we have a smattering of significant voxels in this case. In general, we would assume that we wouldn't have any significant voxels because the data is generated with mean 0. So all these white voxels are false positives. So there's approximately 500 false positives, as one would expect, because we're saying when we're thresholding at the 5% level that we'll make a mistake and erroneously have a false positive 5% of the time. So 5% out of 10,000 would be 500. So the threshold u equal to 1.645, while it's good for an individual test, it's not good for a family of tests, such as the one illustrated here. Now, in order to control the family-wise error at 0.05, the Bonferroni correction states that we should threshold using each individual test using 0.05 divided by 10,000. So this corresponds to a threshold of u equal to 4.42. If we threshold every voxel using this particular value, then we get no false positives at all. So basically, we correctly see that there's no activation going on in this kind of cartoon image. Indeed, if we were to repeat this procedure 100 times, on average, only 5 out of every 100 generated data sets in this fashion would have one or more values above u. So that's how stringent the family-wise error rate is. It says that if I'm controlling the family-wise error rate at 5%, on average, only 5 out of every 100 times I perform this experiment, I'll get one or more false positives. So that's a very strict control over the number of false positives. The Bonferroni correction is known to be very conservative. It results in very strict significance levels. It will decrease the power of the test, so the probability of correctly rejecting a false null hypothesis, and will greatly increase the chance of getting a false negative. So we're going to get very stringent thresholds where we might get a few active voxels, but a lot of the active voxels, truly active voxels, might not pass that threshold. So in general, it's not optimal for correlated data, and most fMRI data has a significant spatial correlation. So we may be able to choose a more appropriate threshold by using information about the spatial correlation inherent in the data. So random field theory allows us to incorporate the correlation into the calculation of the appropriate threshold. And so what this is based on approximating the distribution of the maximum statistic over the entire image. So what is the link between the family-wise error rate and the max statistics? Well, the family-wise error rate is the probability of getting a family-wise error. And this is simply equal to the probability that any t-statistic or test statistic exceeds u under the null hypothesis. However, if any t-statistic exceeds u, then the maximum, or the largest t-statistic, must also exceed u under the null. Because if any t-statistic exceeds it, the largest one has to, right? So the family-wise error rate can be written as the probability that the max test statistic is bigger than u under the null hypothesis. So in this situation, what we do is we can find the distribution of the max statistics. We can threshold this at some number u so that it's controlled at the alpha level. So we would choose the threshold u such that the max only exceeds it alpha % of the time. And so this is another way of thinking about the family-wise error rate. So if we can approximate the distribution of the max statistic, well then we can control the family-wise. We can use this to control the family-wise error rate. And so this is where random field theory comes into play. So random field theory has a very rich mathematical background. It comes from the area of topology, but it was found to be useful in controlling for family-wise error rate as well. So a random field is a set of random variables that are defined at every point in some d-dimensional space. And so what we're most concerned with here are Gaussian random fields. And so Gaussian random field has a Gaussian or a normal distribution at every point and every collection of points. And so a Gaussian random field is defined by its two first moments, so by its mean function and its covariance function, just like a normal random variable. And so we consider these statistical images that we obtain to be a latest representation of a continuous random field. And so using random field methods, we're able to approximate the upper tail of the maximum distribution. And this is really the part we need in order to find the appropriate thresholds. And secondarily, it allows us to account for the spatial dependence inherent in the data. So it allows us to do something we can't do with standard Bonferroni correction. So let's talk a little bit about random field theory. So let's consider a random field Z of S to be defined on some d-dimensional space. So usually d is equal to 3, so because the statistical image is in 3 dimensions. And so here's an example of a random field in 2 dimensions. And so here we have a heat map on one side, and on the other we see kind of a 3-dimensional representation where the z-axis is the amplitude. So one of the things that we're interested in about this random field is something called the Euler characteristic. So the Euler characteristic is a property of an image after it's been thresholded. So after we've kind of binarized it and given it values 1 if it's above a threshold and 0 if it's below a threshold. So what the Euler characteristic does is it basically counts, a little non-technically, the number of blobs minus the number of holes. And at high thresholds it just counts the number of blobs in the thresholded image. So to illustrate, let's look at the 3 images to the right here. So we have a random field, and let's say we threshold this random field at a value u equal to 0.5. And every value that's above 0.5 is shown in white, and every value that's below 0.5 is shown in black. In this case, we get the following thresholded image here. So what the Euler characteristic is a property of this thresholded image. It's basically telling us, well, how many blobs, so how many coherent regions are there in this, minus how many holes are there. Well, if we count, then basically the Euler characteristic here is 27, because there's 28 of these blobs, and there's 1 hole. You see here there's a hole in this blob. So that would give us an Euler characteristic of 27. If we increase the threshold to, say, 2.75, now only 2 clusters survive the threshold. And so the Euler characteristic there is 2. There's 2 blobs and no holes. And then finally, if we threshold at 3.5, only 1 small blob survives, and we get an Euler characteristic of 1. So while this is interesting, it's still unclear how this is useful for controlling the family-wise error rate. So in order to do this, we have to find a link between the family-wise error rate and the Euler characteristic. And we do this by expressing the family-wise error rate, again, as the probability that the max test statistic is above some threshold u under the null hypothesis. So if this is true, this means that we're going to have 1 or more blobs, right? So if we threshold the image at u and the maximum statistic is above u, that means that that statistic value will be white in the thresholded image. And so we'll have at least 1 blob in that image. Let's assume, for sake of argument, that no holes exist. In that case, this is approximately equal to the probability that the Euler characteristic is bigger than or equal to 1. Now, if we further assume that the threshold u is high enough that there's never more than 1 blob, well, then this is approximately equal to the expected Euler characteristic under the null hypothesis. So here we have a very interesting link between the family-wise error rate and the expected value of the Euler characteristic under the null hypothesis. Now this seems like we've complicated the problem an awful lot. So now, in order to calculate the family-wise error rate, we need the expected Euler characteristic. But here's where the good news comes into play. Because of all this research on random field theory, closed-form solutions exists for the expected Euler characteristic for Z-maps, T-maps, F-maps, and chi-square continuous random fields. So there actually exist closed-form solutions that we can use to control the family-wise error rate. So for 3-dimensional Gaussian random fields, for what's called large search regions, the expected Euler characteristic is approximately equal to this kind of ugly formula here. Here R is equal to V, which is the volume that we're looking at, divided by the full width half maximum in each of the three dimensions. That represents the smoothness in each of the dimensions. So here, V is the volume of the search region, and the full width at half maximum represents the smoothness of the image estimated from the data. So this term R, which is often called the resolution element, or resol, tells us a little bit about how many independent entities exist within this volume. And so the smoother the image, the smaller R would be. So using this results, we can say that for large U, the family-wise error rate is approximately equal to this same result for some fixed value of U. Now this is kind of a difficult formula to process, but if we look at it, we see some interesting properties. For example, as the threshold increases, and this U increases, and this U increases, this term is going to decrease faster than this increases for large U's, and so as U increases, the family-wide error rate will decrease. So as the threshold becomes more and more stringent, the likelihood of making a family-wise error rate will be smaller. And so that's very natural, and that's a good property that we want. Similarly, as V increases, so the number of voxels over which we perform tests over increases, the family-wise error rate will increase as well, because R becomes bigger, and as R becomes bigger, so does the family-wise error rate. So basically, the more voxels we compare over, the bigger the family-wise error rate. That's also a reasonable property. Finally, as the smoothness increases, the family-wise error rate will decrease. So as the smoothness increases, these full width half maximum terms will become bigger and bigger, and R will become smaller and smaller, and in turn, the family-wise error rate will become smaller. So the smoother the image we have, the smaller the family-wise error rate is. And this is a reasonable thing as well, because if a lot of voxels are behaving in a similar manner, we have less kind of independent tests that we need to perform. So in sum, even though this formula looks not so intuitive, when we break it down, it makes a lot of sense. And so what we can do in this case is, if we want to control the family-wise error rate at, say, 0.05, we can find a value of U for which this entity is equal to 0.05, and that will be our threshold. Now, random field theory makes a number of assumptions. For one, the entire image is either multivariate Gaussian or derived from a multivariate Gaussian image. Two, the statistical image must be sufficiently smooth to approximate a continuous random field. So the spatial smoothing that we apply must be, the full width half maximum of that smoothing kernel must be at least twice the voxel size. So in practice, we have to spatially smooth the data before applying Gaussian random field theory using maximum of about 3 to 4 voxel sizes. Third, the amount of smoothness is assumed known, so the estimate is biased when images are not sufficiently smooth. And four, as you saw, there were several layers of approximations that went into getting this result. However, even though random field theory seems quite esoteric, it remains kind of the dominant way of controlling for family-wise error rates in the neuroimaging community. And there are other ways of controlling family-wise error rate as well, such as permutation tests that tend to perform better, but because we have these closed-form solutions for the random field theory, they provide us a very simple way, a very quick way of controlling for family-wise error rate. And that has probably led to a lot of their popularity. Okay, so that's the end of this module. Here we talked about using the family-wise error rate correction in order to choose an appropriate threshold for neuroimaging. And we talked about different methods such as the Bonferroni method and Gaussian random field theory. In the next module, we'll talk a little bit about false detection rate, which is an alternative way of controlling false positives. Okay, see you then.